Hey guys, welcome to Unit 2. In this unit, we're going to be talking about derivatives, and we're going to find all sorts of different ways to find them algebraically and graphically. But first, obviously, you're going to learn what a derivative is. Before we actually get into the definition, we're going to be estimating the derivative and then talking about when a derivative wouldn't exist. So first, I'll start with kind of what a derivative is. So the derivative, and you can read all about it here on this first page. The derivative basically measures rate of change of a graph, but it looks at the rate of change at a particular moment. So a lot of times you're going to hear us describe the derivative as instantaneous rate of change because it's happening at one point. So finding the rate of change or slope at a point probably seems a little counterintuitive because we've always been using 2 points to get the slope, right? Like you would find the change in y over the change in x and so on and so forth. So for the derivative, once again, we're going to talk about what's the slope through that point. And so that slope I'm looking at is the tangent to my curve. So you'll notice if I change where the point is, like if I put my point over here, then the slope to the graph through that point would be a much different line than the other tangent. So clearly, as we move along the graph, we can have different slopes depending on where the point is. So we're going to look at that. But first, let's just start by looking at some estimations. So if we used our calculator, so here's our function f of x. And if we want to find the derivative or the slope through 1, which is what we've got here, notice that notation, f prime of x is going to now be known as the derivative of f. So the slope through f, if you will. So, okay, so take a look at this. I put this function into my calculator and I went to my table and plugged in a number very close to 1 on either side. So in theory, if I want to find the slope through 1, I can find points very close to 1 and find the slope between those. So that's what I'm doing here. So I'm just going to do change in y over change in x. So I've got 1.004 minus 0.996 over my change in x's. And this is going to be pretty close to 1 because I'm just a small bit on either side. So on top, let's see, we get zero point 0.8. On the bottom, we get zero point 0.2. And so we end up with 4. So that would mean my slope at 1 is probably pretty darn close to 4, if not perfectly 4. Okay, let's estimate it from a table. So if I want to estimate the slope, again, because of the derivative symbol here, through 2.5. So I'm not just plugging 2.5 into my function. If I plug in 2.5 into my function, I just get 3, because see, this is f of x. If I want the slope through 2.5, that's when I have to use my rate of change equation. So I can pick 2 points. So I have some options. I could pick 2.4 and 2.5 and get a close estimate. I could, let's just look at that real quick. So 3 minus 2.1 over 2.5 minus 2.4, and that's going to give me zero point 0.9 over zero point 0.1, which is just 9. So that's the slope on that side. I could also find the slope on the other side. So I could use like 2.6 and 2.5. So here I go, 4 minus 3. 2.6 minus 2.5 gives me 1 over zero point 0.1, which is 10. So the slope on this side is 9, the slope on that side is 10. And so we could say, the slope is probably somewhere between there. And this is, again, just an estimate. Or you could use a point on either side and kind of find the slope there to see. So let's take a look at that. So I'd have y minus y over x minus x, and that gives me 1.9 over zero point 0.2, which is 9.5, which you guys might have kind of already thought might happen. So there's an estimate for 2.5. So there's lots of different ways to get kind of an estimate for it. So then we're going to look at the slope or the derivative through points from an actual graph. And so here I am just showing you some points. So take a look. If I wanted the slope through this particular point here, then I'd be looking at the slope of that tangent line. So notice it's decreasing, so it's negative, and then the steeper I get for that line, the more negative it gets. And then here's me just showing you some examples of some positive slopes. And so again, as your point moves along the curve, it's going to change the slope of that tangent line. Okay, so let's look at an actual example. So this asks me to estimate g prime of 1 or the derivative of g at 1 or the slope through 1 for this function. So here we go. So I've got my point at 1, and if I drew a tangent line in, and I'm just kind of estimating here, this isn't perfect, so let me fix this just a tiny bit. Okay, so there's kind of an estimated tangent line. And it doesn't need to be perfect because these multiple choice answers are going to be different enough that there should only be one that makes sense. So first of all, is the slope through my point at g of 1, which here we are again at 1, is it 0? No, it's not. If the slope was 0, we'd be talking about having a horizontal line. Is my slope negative? Well, this is a decreasing line, so yes. So it's either this guy or this guy, so I can get rid of my positives. So now I just have to look at whether this line has a rate of change of -1/4 or down 1 over 4, something like this, or -2, down 2 over 1. So let's take a look. Down 1 over 4, that doesn't make sense, but down 2 over 1, that does. So -2 would be my estimated slope. Let's look at another example. This one wants the slope at 3. Again, this is not the point when you plug in 3. If I plug in 3, I get 1. I'm asking for the slope at 3. So again, I've got a tangent line. I'm just going to do a rough sketch. Clearly, that line is not horizontal, so it's not 0. It is still decreasing. If it were headed like this would be a positive slope, but it's not. So I can get rid of anybody that's positive. And then again, my question is it down 3 over 1, or is it -1/3, which is down 1 over 3? If I go over here to my graph, down 3 over 1 from that doesn't make sense, but down 1 over 3 makes the most sense. So -1/3. I also told you I'd talk about when derivatives don't actually exist. So we've got a few places where we can't find the slope of the tangent line to the curve, and I think you're going to see why. In the first example, we can't find the slope at a vertical asymptote. There is no graph there, so we can't find the slope if there's a vertical asymptote in the original graph. We also can't find the derivative or the slope if we're looking at a point of discontinuity when it's a jump discontinuity. And that's just because typically the slope heading this way and the slope heading that way are going to be different. So if it's a jump discontinuity, you can't find it. If there's a sharp turn in your graph, you can't, because the slope as you approach that from this way and the slope as you approach that from this way do not match. So any sharp turn in your graph, you can't find the derivative or the slope. And then the last one, and this is probably the most tricky for some people to know, if your slope um, creates a vertical line, that doesn't exist. And the reason that doesn't exist is because a vertical line technically means that your slope was some number over 0. And so that doesn't exist because it just doesn't exist. Like you can't divide by 0. So vertical asymptotes don't exist, jump discontinuities, sharp turns, and vertical tangent lines to the graph. All right, so you're ready to go. We're going to spend our first few problems estimating and then looking at where derivatives exist. See you in class.